All right. We're very happy to have Andreas Stavros telling us about cohomology of configuration space of surfaces as mapping class group representations. Andreas.
Thank you very much, Sam. Let me just share screen. I think it should happen in a second. Okay, it's happening. So I'll be talking to you from my iPad. Thanks very much for the invitation and for having me here. I will be speaking to you about cohomology of configuration spaces of surfaces as a mapping class group representations. So let's see what the structure of the next hour will be. I would like you to stop me if at any point I'm saying something that is nonsense or that doesn't make sense or is, like if you would like a clarification. So, okay, so the structure of this talk, I will start with an introduction where I introduce the terms in the title, configuration spaces, mapping class groups of surfaces, specifically speak about what was known before about their homology and what I am going to, what I'm showing essentially. So everything that I'm going to speak about is from work that I've written up in my first paper that is in the archive now. Yeah, so, okay, that will be in the introduction. Then we'll go into a theorem that holds for all manifolds that computes this homology of configuration spaces in terms of the cohomology of a mapping space from your manifold to sphere. And we'll see that. I will not speak about the proof, but if you want to ask me in the end, I might be able to say something. And then we'll focus on the case of surfaces, and that's going to be the main part of the talk. And yeah, that's when I actually tell you what exactly the answer is. And then, okay, we'll have some concluding remarks, including the action of the Johnson filtration. Okay, so I'll be speaking, all my vector spaces will be over Q. And I will be considering cohomology with rational coefficients, and that will be implicitly assumed throughout. So, introduction. The ordered configuration on a manifold M, or a space M, is the set of n tuples of n distinct points, ordered n tuples of n distinct points on the manifold, and that's topologized as a subset of the product of n copies of the manifold. Okay, now the symmetric group acts on this space by permuting the particles, so we can take the quotient, and that's what for me will be the configuration space of M, or unordered configuration space of M. In the picture, what just changes is that we do not have labels of the particles anymore. Right. Now, if M is specifically a manifold, I can consider its diffeomorphism group, which is the group of orientation preserving diffeomorphisms of M that fix the boundary point-wise. And that's a group that people are interested in generally, but that's a big group usually. So we might want to just consider its connected components. In other words, diffeomorphisms up to isotropy. And that's what I will call the mapping class group of M. Now, the diffeomorphism group acts naturally on configuration spaces. Now, not every map of manifolds would induce a map of configuration spaces, but because it might not be injective, for example. But diffeomorphisms are injective, so they induce maps on configurations. Now, this makes their cohomology into a mapping class group representation. So the question that I'm interested in is, what is this representation? And right, I specialize in the case where M is a surface, compact-oriented surface of genus G, at least one, with one boundary component. This boundary component usually makes things easier. Usually closed surfaces are harder than surfaces with one boundary component. Actually, I am working currently on closed surfaces, but they are like, you have to first do surfaces with boundary. Right, I will denote by gamma G1 the mapping class group of sigma G1. And that's group that lots of people care about. I hope that you also care about it. So yeah, so let's see now. Let's see some facts about surfaces and gamma G1, the mapping class group. Okay, if we write HZ for the first homology of the surface, which is Z to the 2G, we have an intersection product here that tells us essentially how curves are intersecting. And this is a bilinear skew-symmetric non-degenerate form that is a symplectic form. And like throughout this talk, this is how I will be calling the the standard curves, let's say. Maybe the letter will change from E to something else, but I will be calling E1, E2, E3, E4, etc. my curves. This is the standard symplectic basis. And okay, if you want, the intersection product is just evaluates as 1 to these pairs and 0 to all other pairs. And okay, then dualizing it gives this, let's call it an invariant tensor, this omega that is E1 wedge E2 plus up to E2G minus 1 wedge E2G in the second power of HZ. I call that omega. This omega will appear again and again later. Yeah, I think that's all I want to say from here. Now, okay, the action of gamma G1 on this first homology preserves lambda because it's orientation preserving. And that gives us a surjective map to the symplectic group on vector space of dimension 2G. That it's surjective, that's a theorem. The map exists because the form is preserved. And the kernel of this surjection is defined to be, is IG1, called the Torelli group, which is something that people also care about. I will be calling gamma G1 representations that factor through the symplectic group, or otherwise said, that have trivial action of Torelli. I will call these symplectic. And an example of a symplectic representation is just the rational homology of H and all its tensor powers, exterior powers, symmetric powers, etc. Okay, well, the upshot is that symplectic representation theory is well understood. I will not be speaking much about this. Maybe I will be coming back in the end. But whenever we see something like a basis of the form E1, E2 up to E2G, there is an obvious way to act for gamma G1 to act on this in the symplectic way, which is to view this as the basis of H. Okay. Okay, so let's hide the thing in the bottom first. The answer for what the homology of configuration spaces of these surfaces are was already known from the 80s by this paper by Bodenheimer-Cohen from 1888. And it is given in terms of this algebra here that has an exterior part generated by x1 up to x2g and like an extra generator v, and there's a differential, and we take homology, and then a polynomial part here that has generators yi's and w. And we take the I, n part of this algebra to find the ith cohomology of the nth configuration space. So the first coefficient denotes cohomological degree, and the second number of configuration points. Now the bi-degrees of these generators are shown here, and the differential has this 2 omega in it, which is this form that I already showed you earlier. And I like to use the following picture to think of these generators. This is maybe not exactly formal, but I hope that after this short explanation, you will agree with me that it's helpful. Namely, I want to think of the configuration of one point doing nothing on the surface, which is something of dimension 0, containing 1 point, to be W. So 0 is the degree and 1 is the number of configuration points. I want to think of xi as one particle moving along a curve. And for example, x2, because that's the curve E2 that I drew earlier. One particle moving along a one-dimensional curve. Now, if I have a fixed point somewhere and then a particle moving around it, I want to think of this as V. So 2 points, but a one-dimensional configuration. And then if I have more particles, for example, 2 particles moving independently on 2 parallel curves, that's Y3. And for example, if I had 3 particles moving independently parallel along the curve E3, that would be X3, Y3, etc. That's just if you prefer to think of algebras as pictures, but if you are good at remembering this, then please go ahead. Okay. So what I want to do, okay, what I propose to do is to add one more clause here and tell you what the action on the right must be so that this is an isomorphism of gamma G1 representations, because this is an isomorphism of vector spaces up to this moment. And okay, to define an action on an algebra, just like to define a map from an algebra, suffices to define it on generators, right? So I have an obvious action that, maybe, I don't know if it's obvious to somebody who didn't think of this for a year, but my first guess would have been that, okay, I treat the x1 up to x2g as a symplectic basis. I treat the yi's as another symplectic basis. I consider w and v as invariant vectors of gamma G1, and then extend this action to the algebra. That's an action that you can define on this algebra, but does this make the isomorphism here gamma G1 equivariant? Well, probably. Well, we don't know, but there is this theorem by Andrea Bianchi from, in a sense, this is just a by the way remark in his paper from 2020, that the action of gamma G1 on this homology of the second configuration space of the surface is not symplectic. But if the action is, as I said, everything would be like the action would be symplectic on the algebra. So this cannot be true. Let me make it red. So this is wrong. So how do we fix this? You might observe.
Andreas, when you say it's not symplectic, do you mean that it doesn't factor through
Yes.
the action of symplectic group? Okay.
Yes, exactly. Or that the Torelli group acts non-trivially. Yeah.
Okay.
Yes. So, okay. So because of that, this action cannot be the correct one on the right-hand side. Therefore, well, we have to figure out something more. The answer will come through the use of crossed homomorphism psi that is something like the Johnson-Morita crossed homomorphism, and that I will explain more later. But I want you to observe that the 2,2 part of this algebra, at least before taking homology, the generators of, like the linear generators of it, are just the yi's and the xi xj's. So that forms a copy of h and a copy of lambda 2h. There is an obvious action of gamma g1 on h and one on lambda 2h, namely the one that factors through the symplectic group. But sort of like to define a matrix on like a linear map on a direct sum, it's like the diagonal action here plus some extra terms. So psi will be the extra terms that I will tell you later what they are. So that's what I propose to do. And yes, up to this moment, do you have any questions? No? Okay, perfect. So let me move on. Right. Now I'll speak about a theorem that holds for general manifolds. First, let me define a couple of things that have to do with the group of non-zero rationals. I will denote the group of non-zero rationals by Q star. Then I will think about representations of Q star. Let's say V is one. I want to define the K weight space of V, and I want to define it as V with superscript K in brackets as a subspace of V on which every rational number acts by multiplication by Q to the K. Okay, and if V splits as the direct sum of its weight spaces, I will say that Q star acts purely by weights. This might not be necessarily close. I'm not sure. Somebody might know more about Q presentations than me right now. That might always be the case, but I don't know. Anyway, suppose I have a multi-graded algebra on which Q star acts by algebra automorphisms, and it acts purely by weights. That puts a weighting on this algebra that is multiplicative. So there is an extra grading that I'll call the weighting. I'll put it in brackets. I put it in brackets just to remember that it does not contribute to graded commutativity, does not contribute a sign. Okay, cool. We'll see this appearing in a second. Now, okay, I want to speak about the rational sphere. For any topological space, particularly if it is simply connected, we can have a rationalization that is a map to another vector space, to another topological space, sorry, that induces rationalizations on homotopy groups or equivalently homology groups. Now, I pick, like there are different models that you can pick for this. I want to fix a rational sphere for every n, equipped with a based action of Q star, so that it acts by degree, so that Q star acts by degree. And it acts by homeomorphisms, okay? This can be done. And okay, what I mean by acts by degree is that every Q acts by multiplication by Q on the nth homotopy group of the sphere. Such an action, I'll call it a sphere action. They exist. Can give an example. We don't need to do that now, though. Now, if a space is defined functorially in terms of the sphere, then the Q star action gets transferred to that space. And taking cohomology, then we get that there's a Q star action on the cohomology ring. In particular, the cohomology algebra is weighted. Well, if provided that the action is purely by weights. Okay. The good thing about the rational sphere is that we can use these weights throughout. And we don't need to worry about finite homotopy groups of spheres. So there's a two-step Posnichov tower. This I might or might not mention at some point. Right. So with all this, now I can go and state the theorem that computes the cohomology of configuration spaces of manifolds. M must be like oriented at least, but not necessarily closed. But it must be compact as well. Right, now it computes this and not its multiplicative structure, I will emphasize, in terms of the mapping space from M to a sphere of dimension D, that is the dimension of the manifold, plus even number, positive even number. These maps must map the boundary of M to a fixed point. So that's the mapping space that we're considering. There's a shift in degree, and the homology of the kth configuration space is the weight K part of this homology. Now, again, something like this at least was known. For example, maybe if you substituted this by, instead of mapping space, like a certain section space of a bundle over the manifold, or if you remove here the mapping class group equivariance, but I had to do some work to show the mapping class group equivariance. So then, okay, then we'll use this theorem to, sorry, yes, Sam?
I have a question. Are you assuming that M is parallelizable?
No, I am not. Yes, I'm not assuming that. And so maybe you're thinking about, okay, that there would be this bundle, this mapping space here. So, okay, let me just very briefly speak about this. The way to prove it is two steps, essentially. You substitute the mapping space by this section space. And there is an obvious map between the two spaces here if M is parallelizable, but I can give you a map using some classifying spaces, even if it's not. I could speak about this at the end if you want.
Okay, but are you saying that even when M is not parallelizable, the map that you can define is at least homology isomorphism on certain weights?
Yes. It's homology isomorphism. Yes.
Okay.
Yes. Yes, but like even if it is parallelizable, the map is not diff M equivariant somehow if you don't take homology. There's this. Does it make sense?
Okay.
Okay. Right. So given this theorem now, in order to compute the left-hand side for the case of surfaces, it suffices to compute this mapping space of like rel boundary of from sigma g1 to even spheres with its gamma g1 times q star action, or if you want with this gamma g1 action and its weight. And from now on, I'm just this L, I'll set M equals L plus 1 just to make things a bit neater. So that's all I want to say about general manifolds. Any questions about this? No, perfect. So now let's focus on surfaces. So we want to compute the homology of this, the cohomology ring, sorry, of this mapping space with this gamma G1 action and Q star action. I will use a vibration sequence appearing here, and it comes from essentially I'm pushing most of the boundary away from itself, except one point. So that, okay, this smaller surface is sigma G1 dash, but I can treat it as if it's sigma G1. And I can assume that the, essentially I'm taking the diffeomorphism group by an isotopy to just act inside sigma G1 dash. Okay, so that makes no difference for gamma G1. And we can from now on forget sigma G1 dash. But well, before we do that, let's go look at this vibration here. Because the inclusion of sigma G1 dash in sigma G1 is co-vibration, and the restriction here is a vibration. The upshot is that here we have just fixed the behavior at a point. Okay, so the base is just based maps from the surface to the sphere. And what's the fiber? The fiber are maps from this disk over here to S2MQ that with fixed boundary behavior, and that's just omega 2 that's loops 2 of the rational sphere. So now we've got two steps. Compute the base, the cohomology ring of the base with its gamma G1 action and its weights. And step 2, to analyze the stereospectral sequence of this vibration R. Okay, so step 1, the ring. So the base mapping space, I can retract sigma G1 onto its one skeleton. So that's the same as, that's homotopy equivalent to base maps from wedge of 2G circles to the sphere. I take out the wedge to make a product. So that's the product 2G times the loop space of the rational sphere. So, okay, but that's something that we know, the cohomology ring of loops of the rational sphere, that's the same as loops of the sphere. And that's an exterior algebra on a generator X tensor a polynomial algebra on a generator Y. And what's this X and Y? These are like the class corresponding to loopings of the identity map on the sphere and the hop map on the sphere. So I will write mu for this quantity 2m minus 1. And X has degree mu and Y has degree 2 mu. I hope you agree with me that X, like that there is an action, the sphere action transfers to the loop space, and that X must have weight 1 and Y must have weight 2. That X has weight 1, I think, is easy to see. That Y has weight 2, you can go and look at the Pontryagin ring. That is, like, you can turn to homology, look at the Pontryagin ring, and there, that's just generated by the dual of X. So Y must have double the weight of X. Right. So by QNet theorem, we obtain the cohomology ring of this base mapping space from the surface to S2MQ. And that's an exterior in 2G generators, tensor a polynomial in 2G generators of degree mu and 2 mu respectively, and their sphere weights are 1 and 2 respectively. So I think all that remains to compute for this is its gamma G1 action. Right. Now, as for this, gamma G1 acts on the fundamental group of the surface, which is a free group on 2G generators. This gives a map from gamma G1 to the automorphism group of the free group. And by just doing some good bookkeeping, we just need to compute the action of odd of the free group on the cohomology ring of maps from the wedge of circles. And then, okay, then this pulls back via rho. We'll not think about odd Z star G too much other than this slide, but I think it's clear where the action comes from, just because pi zero of automorphisms of the wedge of circles is odd Z to G. Okay, let's see an example of what this should be. If I have an automorphism of the free group on 2 elements, phi, that maps A1 to A1, A2, and A2 just to A2, then we get an automorphism of the algebra, of this algebra here, which is exterior on X1, X2, polynomial on Y1, Y2. And so in order to compute phi star, I must tell you where it sends X1, X2, and where it sends Y1, Y2. Where it sends X1, X2, well, in the degree 2 mu, there's not, sorry, degree mu, there's not too much. It's just generated by the xi's. So a good guess would be that X1 gets sent to the abelianization of this. That is actually the case. And X2, similarly, the abelianization. And, but then in order to compute where the yi's are sent, in degree 2 mu, we've got the generators Y1, Y2, X1, X2. And Y1 gets mapped to this Y1 plus Y2 plus X1, X2 term. And that's because if we think a bit, this corresponds to the pinch map, like splitting like the sphere, circle into a wedge of 2 circles, and that induces the concatenation map on the loop space. So that's, there was some contravariance going there. And then again, some contravariance there gives the coproduct in cohomology. And we know what's a coproduct of the sphere. It's X maps to X tensor 1 plus 1 tensor X, Y maps to Y tensor 1 plus, well, there's this term in the middle. That term in the middle is what gives this. And this was just on one automorphism, but somehow this generates everything in auth Z, the free group on 2G generators. So let's see now how to formalize this for all phi. Okay, I'm fixing a standard symplectic basis on the fundamental group, as shown here. It's the same as before, I'm just like connecting them to the base point. I will define this quantity, that is the content, that maps from the fundamental group to the second exterior power of the xi's. I haven't written here that this sends wi to xi. That's like from pi 1 to h. So that's the rational abelianization map. So what does it do? We write every word here in the alphabet alpha I, and then we take every two letters and take their wedge, essentially. Some ways to evaluate this: on one letter words, this content, the content of one letter words is 0. The content of a single product is just a wedge. The content of a commutator, sorry, is 2 times the wedge. So this is 0. This is 0 in the rationalization, in the abelianization, sorry, but it has non-zero content. And the boundary word has a content 2 omega. That 2 omega will like appeared earlier in the homology and appears again now, and will appear in a second again. Okay, so now I will use this content to define a function from gamma G1 to homomorphism from H to lambda to H. I want you to think of H as generated by yi's and lambda 2h as generated by xi, xj's wedges. Okay, so what do we do? Oh, sorry, this had to be yi. For every phi, okay, my phi before was in auth Z to G. Now we'll take it in gamma G1. Doesn't make a difference. Xi of phi defined on yi is the content of the image of the corresponding letter. That's in lambda to h, and extend this linearly on h. So that defines a group homomorphism on the right, like a homomorphism from h to lambda to h. Now this map xi is not a group homomorphism. It is in fact a crossed homomorphism. And it happens to agree with the Johnson homomorphism on the Torelli group, well, up to a scalar. And in fact, it must be equal to the Morita cross homomorphisms K tilde up to coboundary, if you know what this is. If not, then don't worry. So this xi, what does it mean to be a crossed homomorphism? It means that I will define representation of gamma G1 called the Johnson representation. With underlying vector space, this H direct sum lambda 2H. Again, I want you to always think of H here as generated by the Yi's and lambda 2H as generated by Xi, Xj's, such that every phi acts, well, I'm trying to write here the matrix that I wrote here, that is act symplectically on V and symplectically on W on, if you started by a direct sum of V and W, plus some term given by Xi. Okay, and that actually does define a representation. Somehow the reasoning is sort of convoluted. Like I define this, then I show that this agrees with something else. That something else is already a representation. So J must be a representation, Xi therefore a cross homomorphism. But okay, let's keep things in the order that I've written them down. J is not a symplectic representation, so the Torelli group acts non-trivially, but it sits in the short exact sequence of, sorry, that's not of symplectic, of gamma G1 representations, surjects to H with kernel lambda to H. Okay. Now, as I said before, I want to view J as containing the Yi's and the second exterior power of the Xi's. And it's not like, this is sort of just a computation, essentially, this theorem, that the action on the right-hand side here is given by the symplectic action on the Xi's and the Johnson action on the Yi's, where the Johnson action is just expand to an algebra the Johnson representation. Does this make sense? Because I think I'm done with this part. No? Yes? Okay, cool. Okay, so let's accept this and let's go to step 2 of this argument. We're going back to the key vibration here. And we now know this with this gamma G1 action and weights. This bit here is the double loop space of the sphere. That's polynomial on W tensor exterior on V, where W now has weight mu-1 and V weight 2 mu-1. Sorry, degrees, these were the degrees, and weights are still 1 and 2. And so we obtain the spectral sequence that in the second page is this polynomial time exterior, with the actions being trivial on V and W, the gamma G1 action trivial on V and W, symplectic on the Xi, and Johnson on the Yi's. And that converges to the cohomology ring of what we want. Okay, what's the differential? It's not hard to see that well, I cannot exactly tell you now, but like comparing with another spectral sequence that makes more sense. And the differential, the only non-trivial differential is the 2 mu-1 differential. And out of the generators, it vanishes on all the rest except V, where it maps V to 2 omega. This has to do with the fact that the content of the boundary word is 2 omega. I mean, it has to do precisely with that. So we observe that this expression of that this differential only involves V and W. So the infinity page, you can disentangle this, essentially, put it out of the homology, and you have the homology of only this bit on the right. So the infinity page is this, with weights degrees as from before, the gamma G1 action as from before. Now, are we done? Well, not in general, because what we get from a search spectral sequence is an associate graded object to the object that we started. And taking totalization of that does not give you the initial, like the object we started with. But in this case, it turns out that it's true. And so the theorem B, the second theorem here, is that in fact, the required homology ring is precisely just taking the totalization of the thing in the previous page. It's the same algebra, just with like not a double index there, but just one index there. And the action is as expected, trivial on W and V, simplicity on the xi's, and the Johnson on the y's using the xi's. Okay, so the fact that this does not hold generally, but it holds here, means that there is something to prove there. Now, let's see, I've got not too much time, so maybe I can give you a very quick overview of how this works. And if you want me to tell you later, then I will.
When you say this isomorph, this is not an equality, you mean not as an algebra. I mean, as a vector space over Q.
Sorry.
You don't mean that.
Tell me again about.
You don't mean that it's not an isomorphism as a vector space over Q, but.
I mean, yes, that as an algebra. I mean, but as algebras, or gamma G1 representations. So, yes, this is true as Q vector spaces. Like, sorry, this is an equality as Q vector spaces.
Right.
But not as algebras or as gamma G1 representations necessarily. In this case, it is both as algebras and gamma G1 representations, essentially. Well, okay. Briefly, why this is true. Okay, I've drawn here some stuff. Essentially, this is the bottom entries, let's say. Okay, then let's see. We've got the W's and V's there. We've got the Xi's, Yi's there, and then they just have products in the other region. Do we have things in the same diagonal? For example, let's see. This is in the same diagonal as this, because they both have total degree 2 mu minus 1. But for things to be in the same diagonal, this doesn't happen too often. Okay, but still, okay, whenever you have two things in the same diagonal, if they survive in the infinity page, you have trouble, essentially. That's what's the case. But, okay, after some thinking, we know that the infinity page is generated by W, Yi in this subalgebra that just contains Xi's and V's. Then very, like, badly said, maybe, suffices that I exhibit this as actual subsets or elements of the cohomology ring that I'm looking at, not just as like subsets of the graded, associated graded object. So there's some thought to that, but again, in the end, what this boils down to is to find a spectral sequence, is to find a vibration that has this space in the middle as total space, that is diff equivariant, and then in its spectral sequence, if you draw the infinity page, then I can find one of the W's and yi's, or this algebra lying in the bottom. Let's not discuss this more now, but if you want to ask me later, so I'll skip this bit here and not discuss more about the proof of that. And let me tell you now what the conclusion is out of all this, so that we're done vaguely on time. Right. We apply theorem A, that was a theorem for general manifolds, and theorem B, that was the theorem computing the cohomology ring of the mapping space Rel boundary with the gamma G1 action and the sphere action weights. So I managed to add this final clause here, telling you, giving you this isomorphism now as gamma G1 representations, but with the correct action, that is the Johnson action on the yi. That is, whenever you act by a class on, by like a mapping class on yi, you might have extra xi, xj contributions. And yes, this is a gamma G1 isomorphism. So that's the big theorem here. And I hope that now you understand what the Johnson action is. Now, there is one last bit to this story, which is, this had to be one. So, okay, there's not just the Torelli subgroup, there is a whole sequence of subgroups that form the Johnson filtration to the mapping class group. This is defined by taking the lower central series of pi1 of the surface, which is defined by G0 is just a group, and then taking commutator subgroups. So Ji is defined as the kernel of the action of gamma G1 on pi1 quotient by the ith central subgroup. So the subgroups, these groups here get more and more complicated as I increases. So the kernel of the action gets smaller and smaller, giving a filtration out of which J1 is precisely the Torelli group. So we already knew that J1 acts non-trivially. That was J1 because that's the Torelli group. The J1 acts non-trivially on the cohomology of configuration spaces of surfaces. That was known by Bianchi already. But then a more recent theorem by Andrea Bianchi, Jeremy Miller, and Jennifer Wilson is that this J2 acts non-trivially on the cohomology of ordered configuration spaces. So, well, along the way, maybe we could ask ourselves, so does J2 act trivially or not in the unordered case? And it turns out that the action of J2 is trivial, and that just has to do with the fact that, that Xi vanishes on J2. And that means that the J2 action is just trivial. That's a corollary from the main theorem. And I think that's all I want to say. I finished a bit earlier maybe, but I think that's good. I will leave you with this happy configuration on a torus, and thank you very much for your attention.
Thank you very much. I clap on behalf of everyone. Any question? Or did I ask a question? So if the surface is closed, you don't have this fact that W is D of something, right?
So we don't have that. W is, what did you say?
So the fact that W is D of V, if the surface is closed, you don't have this, right?
You mean omega? You mean?
Oh, is it omega? Okay, sorry.
Yes, it was. There was a W and there was an omega. Sorry. You still do have that, but you have a bit more too. Essentially. Let me go back to.
So why is closed surface harder?
Because okay, this algebra here is generated in degrees 1, 2, and let's say it's 1 and 2, but then somehow we know that we have this. Somehow this is a subalgebra that is a symplectic subalgebra. Okay. Somehow the generation of, somehow the differential is more complicated. Like you have to take a spectral sequence starting with this and adding a differential, an extra differential to do closed surfaces. So you get something more complicated with less obvious like generation properties. Yes. Yeah. So that's somehow what you get. I mean, for example, you have one more generator, U, that is before you take homology. Just like here, V was a generator before you take this homology. But when you take homology, V dies. So there's no actual class V. Okay. In the case of closed surfaces, U is another generator that is the class of one particle moving along the whole surface. So U would have degree now 2,1, like it's a two-dimensional family of configurations with one configuration point. Here, you're not allowed to have particle moving along the whole surface because that would not be a cycle. Okay, so there is one more generator, U, in the case of closed surfaces. And then you take the homology of that with a more complicated differential. So that's what happens in that case.
I see.
But don't you, I thought you had results in the closed case for the stable homology. Is that?
So that's something I'm working on now. And I think that for stable homology, actually the answer is that J2 acts trivially, for example, and I can tell you the configurations. The representations of gamma G1.
Okay.
I do not yet know what the answer is for the unstable range.
Oh, but in the stable range, you think, and
Yeah.
that uses scanning, or what's that? Like, why is the stable part easier?
So the stable part is easier because, how to say, okay, like literally what I have in that case is a spectral sequence, okay, that starts from, let's call this algebra R, okay, that is R, and then there are two columns in it, okay, it's R and U tensor R, okay, that's the spectral sequence that looks like that. So there are just two columns, and so there's an extension problem to solve in terms of representations. I know this representation as a yes.
This wait, is this is coming from like this is like in Oscar's configuration space paper, this like how he proves homological stability with Z mod 2 coefficients. There's this long exact sequence from like including configurations of a punctured surface into configurations of a surface, and then the co-fiber is a suspension of configurations of the punctured surface. This is the same as that.
I think that's the same as that.
Okay.
Yes, I mean the way I get it, I'm working still as I'm using this theorem here in terms of mapping spaces. So I'm comparing the mapping space of sigma G to an even sphere. I'm mapping down to somehow like there's an inclusion of that, and then what is here is sort of a sphere. Like this is.
Oh, okay.
That makes sense. Like it's an evaluation vibration, and the fiber is sort of that.
Yeah, yeah, but this exists unstably, like it's in Oscar's configuration paper.
Yeah. I'm not like I haven't exactly read that paper, so like I just believe that.
Yeah, yeah. I mean, if it's relevant, I can tell you where that exists.
Yeah.
Not on the map side. And wait, what is this oh, wait, you said like it was known non-equivariantly. Where is equivariant means like mapping class group action.
Yes.
Okay. And then isn't this like basically in Bodenheimer, Cohen, Taylor? Maybe I'm confused.
I think it was not equivariant. If it's a paper from the 80s.
They don't consider mapping class group actions, but just like your idea is, okay, you look at configuration space, you view that as like configurations of points labeled in S0, and then, hey, S0 you can replace with an even dimensional sphere as long as you mess with the gradings, and now it's group like, so you can do scanning. Like at least
yes.
Trick from Bodenheimer, Cohen, Taylor's paper.
Yes, that's sort of what I do too. I'm sort of like keeping track of that in terms of equivariance.
Yeah.
And then like untwisting, because then if you want to do that, what you get on this side by scanning is twisted mapping space or a section space. Right? If you do scanning, you usually get a section space over a bundle over M.
Here do you need the manifold to be orientable?
You need this to be orientable. Yes, I see.
Yeah.
Before metaphor, it's right. Yes.
Yeah.
You don't need compact.
Yeah, you don't need it to be parallelizable.
No.
But you need it to be orientable.
Yes. Yes.
Actually, could you explain that why again?
So explain why.
Why non-trivial tangent bundle doesn't matter in this isomorphism?
Yes. Okay, so let's go here. So I guess so. What Jeremy is saying is that this is sort of following the path of Bodenheimer, Cohen, Taylor. So we're happy with that. So we're going to this side now. Okay, so what's the bundle that we have here? Something that is the tangent bundle of M, fiber-wise smashed with like this sphere, I guess. Okay, that's a bundle over M. Like, what's the, how to say? So this is classified by a map to BSO D, right? Now, and okay, but now we don't have SOD just acting on Rn, oh sorry, Rd, but there is also this sphere here. So you can sort of cheat a bit and map. What do I want? I want to consider this as a map, as a sphere bundle, okay? Like as a fibration, okay, as a spherical fibration. So what I'm putting here is homotopy automorphisms of degree 1 based of the sphere S2L plus D.
You use orientability in writing 1 there.
Yes.
Yeah.
Okay. And now, in order to consider sections of this bundle, I can consider now, like, what's the total space of this bundle, like that's a pullback. In order to consider sections here, I can consider the space of lifts of this horizontal map at the bottom, right? And right, the point is that if you take, if this, where is this? Let me change color. If this degree here is even, if it is even, okay, then what's this? This is contractible. This is, yeah, then this is contractible. Because what's BH?
No, I don't think. Oh, I think here's a statement that I'm sure of. H ought of a rational sphere, if n is even, is a 2n, I think, -1.
Oh, but if it's an odd sphere, sorry, maybe I'll be odd.
No, I think you just want it to be even, but then it's like it doubles the dimension. So its connectivity is roughly twice the dimension of M.
No, but
So
tell me if it's odd,
right?
Sorry, if this is odd, is this contractible?
I think H ought of an odd sphere is the sphere itself. Like it's a group and it acts on itself.
The fact that I'm taking base automorphisms. I think the point is that I manage by taking this even to be either to be odd or even to make this space contractible. I don't remember which one of the two is true because I'm taking the rational sphere. And I'm not actually using this 2L plus D. I'm using something maybe one dimension lower just to make sure that it's even or odd.
Yeah.
And
I guess couldn't you just make D is D the dimension of the manifold, or
yes.
Oh, D is the dimension, yeah. Oh, so you can't change that. But I think when it's even dimensional, it's just going to be highly connected.
Okay.
if you don't take the base point condition, it's going to be highly connected enough that
Okay,
like
so
the
I see.
compactification of a tangent bundle is always rationally trivial if it's but I mean there's an interesting thing that I'm pretty sure if you fix a base point, it's not trivial. It's not trivial bundle. Like there's an interesting like you know, so if you look at like the scanning map from configurations of k points,
yes,
so like the section space of degree k, and then you say, okay, that section space is the same as maps to a sphere, but it won't be the same as maps of degree k maps to a sphere. It'll be like degree k minus 2 times the Euler characteristic of the manifold.
yes, yes, yes.
And that has to do with the fact that it's like a trivial bundle, but not a base trivial bundle, or trivializing it is going to mess up your section, and degree is intersection number with the section.
Yes, I know exactly what you mean. I know exactly like which part of your paper with Bendersky you're referring to.
Oh yeah.
I think. So that does not play a role here somehow. So somehow I try to get around doing that you're doing in that paper, but making sure that I do not run into trouble. So let me just look at my paper for a second to just make sure that I'm not saying nonsense.
Also, people should feel free to leave. Are we still being recorded?
Yes,
Maybe we should.
we can stop it. Right, so I'm gonna stop the recording.